Hey everybody, this video lesson is going to cover naming basic ionic compounds. Naming compounds is when you're taking a group of symbols and converting them to words. Naming ionic compounds follows a very repeatable system, and once you know the system, you can apply the system to all types of basic ionic compounds. Let's start with the basics. What makes an ionic compound ionic? Well, an ionic compound has a positive cation and a negative anion. The name is always written cation first, anion second. Now the cation is typically going to be a metal, and that metal is either going to be in a group 1 or group 2 metal. Another option may be aluminum. Aluminum may be used in this case as well. So these are basic metals from group 1 or group 2. Now basic ionic compounds do not cover transition metals. That will be covered in a different video lesson. Now the anion, on the other hand, is typically going to be a nonmetal. And this nonmetal will be made up of one atom. Examples include fluorine, chlorine, or oxygen. Now let's say you have an example like NaF. Here are the rules that you use to name this basic ionic compound. 1. The metal always just keeps its name. And when I say metal, that goes for the cation. The cation may not be a metal, it may be hydrogen or a polyatomic ion known as ammonium, which we'll again cover in a future video lesson. Now a word about hydrogen. If hydrogen is listed first in the compound, it is acting as a cation or a metal. And so it has a +1 charge, just like any other metal in the first group of elements. Now as far as the nonmetal is concerned, the nonmetal fluorine drops the ending and adds IDE. And this is the same thing you would do for all ions that are made up of a single ion. So if I go ahead and name this over here next to NaF, I'll name it sodium fluoride. Again, the metal keeps its name and the nonmetal drops the ending and adds IDE. Let's scroll up and do a couple more of examples. Now here are 3 more ionic substances, MgCl2, Al2O3, and K2O. They are all made up of a metal and a nonmetal. Now it's important to note, and I didn't mention this yet, but the quantity of the ions does not ever affect the name, because ionic compounds always combine so that their charges have been canceled out. The ratio of Mg to Cl is always a 1:2 ratio. For aluminum and oxygen, it's always a 2:3 ratio, and potassium and oxygen is always a 2:1. So you do not need to worry about how many there are. The metal keeps its name, the nonmetal drops the ending, adds IDE, and there is no mention of using a prefix like a mono or a di or tri in order to determine how many there are. You just simply write the metal and then the nonmetal. So this first one is magnesium chloride. The next one you see, Al2O3, is aluminum oxide. And finally the last one, K2O, is potassium oxide. Again, the quantity of the ions does not affect the name at all. Now what about the reverse process, writing formulas for basic ionic? In this case, you are given the name and asked to write out the formula, making sure that the quantity of the ions balances charges. The whole goal of an ionic compound is that the ions will combine in a way that the charges cancel each other out. And so there's basically 2 steps in this process. The first step is identify the charge of each ion. That includes both the cation and the anion. The second step is to balance the charges using basic math. Here's an example of one that you'll need to write out from name to formula. Sodium sulfide. So the metal, sodium, is just the symbol Na. And the charge on that sodium is a predictable charge because it's in the first column of the periodic table. And these metals, if they're in the first column, they're a +1 charge, and if they're in the second column, they're a +2 charge, and if they're aluminum, they're a +3 charge. So sodium's a +1 charge. As for sulfide, you can find its symbol S, and its charge can be predicted very similarly to the metals. All the nonmetals that are in the periodic table lie in a column, and the column has a predictable charge. Because sulfur has 6 valence electrons normally, it will gain 2 electrons to achieve 8 valence or a full valence energy level. And if that's the case, it becomes a -2 charge. So the key to identifying the charges is using the periodic table and identify the position of each ion and determine how many valence electrons it has and whether or not it will lose electrons or gain electrons to achieve a full valence shell. Metals lose electrons, nonmetals gain electrons. Now once you've got this step of identifying the charges, next you need to balance the charges. So you got to think to yourself, if I have 1 sodium and 1 sulfur, I'm going to have a -1 left over because +1 minus 2 is a -1. So if I just basically double my sodium, then I'll have 2 +1 charges for the -2 sulfur. And so you simply take the number and put it down behind the sodium, like this, and you get rid of the charges and smush it together, and you get Na2S, without any space between the metal and the nonmetal, and that is the correct formula for sodium sulfide. Now let's do a couple more examples. First, let's take on lithium fluoride. So lithium is a +1 charge ion because of its position on the periodic tables in the first column. Nitride refers to the nitrogen ion, and nitrogen is in group 15. And group 15 all have 5 valence electrons, and so they need to gain 3 to get 8, or in other words, nitrogen has a -3 charge. Now think to yourself, how many of the pluses do I need to balance out the nitrogen? In this case, I need 3 pluses to balance out the 1 minus 3, and so I have Li3N. Let's tackle calcium chloride. Calcium is a +2 charge ion because of its position on the periodic table. Chloride is a -1 charge. Chlorines in group 17 of the periodic table, all those elements known as the halogens have 7 valence electrons, so they'll gain 1 or become a -1 charge. Now you have a +2 charge and a -1 charge. How many of the negative charges do I need to balance the plus charge? The answer is 2. So you put a 2 down behind chlorine, eliminate the charges, and smush it together. And you get CaCl2. Now the last one's a little bit tricky, but I'm going to show you a little trick that you can use so that you get the formulas right every time. Aluminum's charge is a +3, and oxygen's charge is a -2. Now what you can do is take the charges of each and cross them down to the quantity of the opposite ion. So the 3 from aluminum goes down behind the oxygen, and the 2 from the oxygen goes down behind the aluminum. And you get rid of the charges and smush it all together, and what you get is Al2O3. Now this is known as the crisscross trick, and it works almost every time. If you take the charge of the cation, make it the quantity of the anion, and you take the charge of the anion, make it the quantity of the cation, you get the right formula. The only thing you need to worry about is when you're doing the crisscross is if you ever come across a situation where you have 2 ions that are the same charge but opposite. For example, calcium oxide. You write out the charges of calcium oxide as Ca+2 and O-2. Now if you crisscross these down to the other side, you'll get Ca2O2. But ionic compounds always reduce to their lowest ratio. So if you can take the quantities and divide them by the same number, do it. Ca2O2 reduces to just CaO. So ionic compounds always reduce to their lowest ratios. Well, that takes care of this video lesson. Thanks for listening.